our semester. This is the first talk in the semester. You already have a schedule of the seminar up to the beginning of June. By the way, let me recall you that we have a special session for young speakers organized in this semester. Maybe it's 30th of May, and everybody is encouraged to invite his or her young master students to make talks on this session. Okay, now let's go to the topic of our consideration today. Today, our speaker is Qingsong Wang from Jilin University, and his talk is named The Geometry of Gaussian Random Curves. Please, Qingsong.
Okay, thank you very much, Professor. Okay, let's begin our talk today. As Professor says, our topic today is geometry of Gaussian random curves. To begin, we first see a picture. This picture is the DNA. I guess everyone knows, and we know that the DNA is a kind of polymers. Since we see such a picture, then I will give the motivation of our work. In physical and chemical science, people usually use random curve to describe polymer which changes with time. The reason of changing is that, first, there are flexible chemical bonds between monomers. Second, there are influence of external force, like random contacts with the molecules of media. Last one, there are interaction between the different parts of polymers. So it is very helpful to use the random curve to describe polymer model. And one of the possible mathematical description of linear polymer model is a random curve can be characterized by such a continuous random process. But usually the random process is non-smooth and our curve will have complicated fractal structures. Then I will show you a picture about it. Yeah, this picture shows a random polymer. You can see this, the structure is really complicated. And we know that the shape of the polymer will changes with time. This is one. And the next is just a picture of the Brownian motion, that it will also change with time. Since we get this motivation to give us the interest to our work, and then I will give you the reference about random curves, which has a model for linear polymers. This first one lectures on probability theory and statistical, and the second is the random polymers. This book will be really helpful for you to understand the model of polymers. Since we get the motivation, then we'll come to give the polygon and the shape of the curve, which is mainly about some initial definition and some explanation. First, we suppose the curve is parameterized by the continuous function. Here we note as phi. And here we have several points U1 to Un, which is in the space R3. We denote such a polygonal line, a big gamma U1 to Un, which subsequently connect these points. We will have such a definition. Our polygonal line is inscribed in the curve if there exists this sequence of time during the interval 0, 1 such that our function phi tk will equal to this uk. To understand this definition, I will give you a picture. This is just a simple one. This red curve, red one is the curve, and this black one is our polygonal line. We can see in this part, our polygonal line inscribes the curve Gang. Next, we can see this is a picture about face recognition. Since we get the definition of the polygonal line inscribes the curve, it's just naturally to raise such a question. How about if the shape is very complicated? How one can characterize it? Just like this, a picture on the face. The idea is that let us forget the monomers of the shape, but we just focused on the main feature of the shape. Just like this, several points on the shape. This human face, when the system recognizes your face, it doesn't follow from every detail on your face. It just like this picture, just follows some special place, this point, and then it will connect this point to be a map. And this is, the idea is exactly the same as the inscribed. So this gives us a good example. Then we go further step, we give another definition. The polygonal line, it inscribes the curve up to the epsilon, which here it has the vertices from the set. This is the set. This set is the union of these small balls. And if there exists a k, which is from 1 to big N, that the uj will belongs to this small ball, then we will say it inscribes the curve up to the epsilon. Then we have that our epsilon greater than 0, such that what we consider is a small ball, which the intersection is equal to empty. Then with every polygonal line, which have the vertices from the set, then there will have a sequence of numbers alpha 1 to alpha n can be associated, and here the uj will belongs to this ball, which the radius is epsilon, and centered at this z alpha j. If we have such a form, we can say this polygonal line has the type alpha 1 to alpha n. Then I will give a picture to explain it. If our curve is inscribed if the polygonal line inscribes curve, and the polygonal line have a type maybe from Z1, Z2, Z3, Z4, it will keep our curves will always go through this small ball. So this is the definition I want to give us. Since we get the definitions above, we now turn to talk about the main question of our talk today. First one is that to estimate the probability that the polygonal line is almost inscribed in Brownian motion, in Brownian trajectory. The second one, to investigate the conditional distribution of the trajectory when the line is inscribed to it. Let's begin with the first question. The first question, we can see it, the subsequent visits Brownian motion. Then we give such theory. We considered Vt is Brownian motion, And the dimension we consider is greater or equal to 3. X is the start point of our Brownian motion. Here we give a sequence of fixed points Z1 to Zn. Then we give a asymptotic of our such probability that our Brownian motion will go through this for Z1 epsilon and Z2 epsilon to the Zn epsilon. We give such beautiful asymptotic. Next, we give the
do we
proof
assume that balls have empty intersection?
Yes, exactly.
Thank you.
Okay, let's continue to give the proof of our theorems. First, we just start from the simple case. We don't discuss a sequence of balls. First, we just considered there's only one ball, which the radius is epsilon. And I just draw a simple picture to show what this probability means. Then we consider such a probability. The first is just to change the coordinate. And then we change the start point from x divided by epsilon to x divided by epsilon minus the z divided by epsilon. The last line of this is just use the scanning property of Brownian motion. So we can change here inside the T. Since we change our probability, then we consider such 3 events. Seeing these 3 events, it's natural to get their relationship. The A1 will be the A2 U of A3. So we can get such a sequence of inequality. This probability will be greater or equal to the probability we want to get is this. And this will be greater or equal to this probability minus another. Our goal is to prove that this probability will greater or equal to some say multiplies here, some say multiplies this and this, and will also less or equal to some say multiply these 2 parts. So first we will estimate this, but this is to estimate this is just some known result that this probability will just the same to this. If one is interested in it, you can find this result on the book Brownian Motion, which is written by Peter. Yeah, and we can see it here. This part is a gamma function, and this is just some simple constant. Since in the gamma function there is just a d, and this d is just our dimension, we can think it's just a constant only connected by this d. So we can say our probability will always less or equal to some constant. Multiply this. So we finished the first part of our proof. Next, we just want to prove this part. And for this probability, we already get. So we only need to estimate this. To estimate this probability here, we use the Markov process, and we just use some change of variable. We see here this process is beginning of Brownian motion start in the origin, and then use the Markov property denote this psi to be like this, and then we denote its density to be peak psi. Okay, here we just use the macro property here to change it to be like this. And then we use this psi to replace it. And we say it also start from the origin. So we get such probability. Then we go further. To estimate this, here we use the condition of conditional expectation. Here we get such expectation. And then we change the expectation to be the integral of the property or the probability. Here is the density of our psi. And to deal with this part, we use the last exit formula. We change it to be an integral on the surface 0, 1, and multiply the equilibrium measure and multiply the Green's function on the surface. And we know that the equilibrium measure is just the uniform distribution on the surface 0, 1. So we can see this integral is equal to 1. And then we give the formula of Green's function. The Green's function is just equal to the integral of the transition density. Next, we just take our Green's functions formula in, and here we can write it to be like this. And we care about this part. Sorry, does anyone have questions? Okay, maybe we can continue.
Yes, continue. Maybe it is not very good connection so for somebody. So please continue.
Okay. Here we see this integration. We can see this is a density. This is a transition density. So we say this integral is just a convolution. So we can denote this to be a new random variable. We denote it to be the beta t. So since we have such a denote, we can rewrite this to be just one integral about the density of this beta t here. And we take the density of beta t here we can get such form, because here is t plus 1 divided by epsilon square. So here we will change it to be. Then here we deal with the integral. We change the variable. We change it to be simple 1 divided by s. And then we can see this integral. We focus on this first. We can see this is already what we want to get. This is because the epsilon is sufficiently small, so here just can be seen as the norm of x minus z to the power of 2 minus d multiply the epsilon to the power of d. So, and because we considered is one probability minus this estimate, so, and this is already the same as before, so we consider this minus. Here we just, because this is just the gamma function, we take the gamma function in, and then we can say this is just the integration is, which the area is greater than this. For the inner part, they are same. So we can straightly get this integration. And we can see here, the x and the z are fixed poles. So there is no variable unknown in this integral. So this integral is must equal to some constant. From this, we get another inequality of our probability will always greater or equal to some constant multiply this. From all of this, we can get the asymptotic of our simple case. Will always have such form. Then we go further step to consider the general case. Still, the
I'm sorry,
dimension.
I have one question, but if you return to the previous
Okay.
slide, this constant C small depends on X.
It's different. Yes, yes. But the S is during this part, right?
Yes, but still depends on X in some way, so it may influence the final expression.
It does depend. Of course, it depends on initial point. Yeah.
It depends on Z minus X, the norm of this expression. So maybe you cannot write this is greater than or what?
Yes, yes, it depends. It depends on.
So you may add something to this 2 minus D or subtract.
X minus Z.
It's kind of small, right?
Yes, you're right, but we discussed this several times, and if Z minus X is bounded by something, then we have no any problem here. Yes,
So,
even more. If Z minus S became to be small, Z minus norm of Z minus X became to be small, this goes to constant. Yeah, so it's okay.
this goes to constant. Okay, yes, yeah, thank you. Thank you.
Yes. This
Okay,
just
let's continue.
Yeah, fixed, right? Okay, let's continue. Consider the general case. Still, the dimension is greater or equal to 2 to 3. X is a start point. Here we consider the sequence fixed point Z1 to Zn. So here we need to get the asymptotic of such probability. Here we use mathematical induction. We assume that we already get the answer when we consider the condition that when Z1 to Zn minus 1, we already get the asymptotic. Then we consider this if we have nth small ball. First, we denote a sequence of stopping time. It will be the first stopping time to hit the small before to hit the next one. Then we use the property of conditional expectation and the Markov property. We rewrite our probability to be such to expectations multiplied. And here we can say for the first part is just the case we only considered a minus 1 small ball. This is our assumption. So we only care about this part. And we consider this be tau prime n minus 1. It's just hit the small ball bzn epsilon. Not, it's just hit the bzn minus 1 epsilon. And so because the epsilon is 10 to 0, so here we use the zn minus 1 instead of this. And we consider this expectation, it's just similar to what we considered in the simple case. The only difference is just the start point here we consider to be zn minus 1, and we will go through the Zn. And here is another different. We used to think just less or equal to 1. Here, we considered it to be 1 minus the tau prime and minus. But we consider it, but it just influenced the result of this expectation in the C. If we consider such an expectation, we can also get some result of C multiply this, the norm of Z and minus 1 minus Z and 2 to the power of 2 minus D. It's just to change the C. So we can also get the asymptotic of our case. We'll got such beautiful kind result. So maybe this is all of the proof about our first theorem.
Maybe before you go further, let me comment this formula, because usually we make comments at the end of the talk, but I want to point attention of the audience to this formula from the following point of view. If you remember, this Z1, Z2, and so on, Z indexed by n, are playing the role of the vertices of the polygonal line which we want to inscribe in our Brownian trajectory. For further consideration, we want to characterize, at least roughly, shape of the trajectory using this polygonal line. And you see, it occurs that it has like weight. And everybody, of course, recognize here the potentials. In case d equal to 3 Newtonian, this is, in case d equal to 4, you have almost Newtonian potential here. So it will be interesting in the future to put into correspondence to the polygonal line, which is inscribed in the Wiener trajectory, or more general in Gaussian trajectory, put into correspondence some energy. And I think that this energy will be related to the potential of some field in the Euclid space. This is the idea for future considerations. Okay, let's go further.
Okay, thank you very much.
May I ask a short question? Unfortunately, I didn't pay any attention on D. What is D in the formulation of the statement? Do you assume here that D is larger or equal than T, or D also can be equal to 2?
No, larger or equal than 3.
Yeah.
3. What happens in 2? Should you have something like logarithm there?
You see, it was also the question, because in the dimension 2, the notion of logarithmic potential and equilibrium measure differs from the higher dimensions. So it is also open question for us.
Okay, thank you.
Yeah.
And Brownian motion is transient if d is greater than 3 and recurrent.
Of course,
Yeah.
this is the key. Yeah, this is the key.
Yeah, we need the Brownian motion to be transient. Okay, I guess we can go further. The next, we'll talk about the conditional distribution. First, let's discuss the distribution of Brownian motion when polygonal line is inscribed in it. We start to consider this case. Here's the capital T is the independent exponential time. We consider our Brownian motion to belongs to some small part theta. And under the condition that before this capital T, it will hit some small ball B, Z, epsilon. Next is a picture shows what the probability means. Here, since we say here, our small data is just a part of this big ring, right? We can see it. So then we just, if we consider in such a ring, we just need to discuss the norm of our boundary motion. Since we get this, so we can use to think about the Bessel process. Then I will give a theorem about the Bessel process. Here this RT2 is the Bessel process, and here this 2 means we considered it in 2-dimensional case. Okay, here still X is the start point of our Bessel process, and this capital T is just an independent exponential time. In our probability here, the dz is a small interval around the point of the stopping time to hit the small level y. We get a simple estimate of this probability when our level y is 10 to 0. Here we notice the answer here is K0. This is the modified Bessel function. And here is just the formula of this of the 2 modified Bessel function. Here is a picture shows us what our probability means. We start from X, and then we will go up to the level, or we will go down to lower to the level Y, and then finally at this capital T, we will hit this small interval dz.
Could you please show us the definition again of this conditional probability?
This one, right?
Yeah. So here, and is it possible that you exit from the large ring before time t capital or not?
I don't hear very clearly. Can you repeat again?
No, show your picture, please. Next picture.
Yeah.
So is it possible that your graph like this, so it exit and then at the moment t hit dz? Or
so you mean like this one, yeah?
Yeah, like my blue.
Yes, of course.
Yes, exactly. Yeah. Yeah, I just draw a kind. It just need to hit the small level.
We just need to visit this corridor, yeah?
Yeah.
Yes. Okay, thank you.
Okay. Then let's continue. We give the proof of our theorem. So to estimate this probability, we know this is a conditional probability. We just write it to be one probability divided by another. And these 2 probability is considered in Bessel process. There are some known results on this book, the handbook of Brownian motion. We can check it on the book. It gives the formula of this 2 probability like this. And as I introduced this K and this I mu is the modified Bessel function. And here the mu is defined by this. d divided by 2 minus 1. And here the d is the dimension. So in our case, the mu is equal to 0. So we just take these two probability, the formula, into our goal. Then we can get such a form. We can notice it here, because we considered the limit of when y tends to 0. But for this part, it doesn't depend on y, only this I 0. So we just need to estimate this. Still use the result in the book, the handbook of Brownian. There is some estimate when y tends to 0, that the modified Gaussian function will have such an estimate. And then we just calculate this. We can easily get this limit will equal to, will just tend to 0. So we can rewrite our estimate to be like this. We can erase this, it's just equal to 1. So we get our result like here. And since what we consider here is the z and the parameter gamma is greater than 0, and use some known result about the modified Gaussian function, this k0 must greater than 0. So what we get, the density is positive. So this finished the proof of the second theorem. Since we get the theorem, we start to think about we return to consider the Brownian. Maybe first we can see this picture first. We used to consider the ring because the dz can be seen as such a ring, right? If we consider the Brownian motion start from x, go through the ball b z epsilon, and finally at capital T, it hits the small theta. It will be such. The trajectory will be have such a form. So we consider such a probability that our Brownian motion will hit the area during the race, and we denote it to correspond to the angle of 1. It's just like this. This angle will denote to be of 1. And then we get the estimate of our probability that the Brownian motion at capital T to hit the small area theta, and under the condition that during the time 0 to capital T, that our Brownian motion will go through the small ball B0 epsilon. We have such an estimate. Here we can say this is just the result of what we get in the theorem. The only difference is here. So the proof is just simple. We just need to consider this. The proof is mainly about some explain of the words. Here we think to divide our annulus uniformly to several parts. Here we just divide them to be every part to be the theta. They will be uniform, and because it's uniform, so each part will also correspond to the angle of 1. And we consider the Markov property. We consider the Brownian motion start from the boundary of the small ball BZ. We considered it start from here, but because we consider the epsilon is sufficiently small, we can say it just like the Brownian motion, start from the center of the small ball, just the point there. And it's also the center of the annulus. So if we consider the Brownian motion start from the center of the annulus, it will have an equal probability to hit every part on the annulus. So we can get such estimate. We use alpha1 divided by the 2 pi and multiplies the probability we considered in the theorem. Because in the theorem, we just consider to hit the dz, the dz considered in Bessel process. But if we considered it in Brownian motion, it will be such an annulus. So we get such an estimate. So that's all for the proof about the corollary, and that is almost all of our talk today. Thank you very much.
Okay, thank you. This is a time for questions and comments. And let me say a few words. That of course, this is just a beginning of the work, because actually our aim is to find appropriate distributions on some family of polygonal lines which can be inscribed in a Brownian trajectory. After this, to have a conditional distribution of all Brownian trajectory under fixed polygonal line. So here we just discussed a very simple case as a beginning when we want to see where the end of Brownian trajectory, and let me recall you that we do some exponential moment of the time. Some work must be done to go back to the deterministic final time horizon. So I think that we began interesting work with Qingsong, and hope that next semester we will see the continuation of this work. Also, maybe somebody have questions or comments, please. Okay, if there are no questions, so we finish our work for today. And again, let me congratulate you with the beginning of our work in this semester. And maybe Georgi know who was the next speaker.
Next speaker is Alexey Rudenko.
Okay, so see you next week. Bye.